Greetings. In my previous lecture, I promised to introduce an easy path into the second law of thermodynamics. What I did was to introduce a property, namely entropy. I said that assume that property, however fictitious, behaves like a property and has all characteristics of a property. And so, uh, special thing about that property is that if a process is possible, that property increases. And if a process is impossible, that property decreases. So just by doing such definition, we were able to write most of this equation. It was a property, so the change of that property within that control volume, very similar to what we had written for energy or for mass, would be a function of the entropy that enters with mass, the entropy that exits with mass during that process. And then, as we defined, then one term would be added, and the change of that property, entropy, would be a function of if that process is possible or impossible. The more possible the process is, the generated entropy would be larger. Then, just to relate this equation to all we had done and um, say why Sgen should behave as we wanted, we related it to the temperature difference that causes transfer. We said that we added one term, which is heat transfer, divided by the temperature of the boundary, and showed with a very simple example how just this very term could behave so that we use the very, very simple and basic fact that heat is transferred always from warm body to a cooler body would ensure that this term would be positive for possible processes. Now, let's talk more about the term entropy and the generated entropy during a process. Now, what we said was that if we draw an axis for Sgen, this is where Sgen equals 0. This is where Sgen is positive, and this is where Sgen is negative. We said that this is for all possible processes, and this part is for all impossible processes, and this point is the boundary between possible and impossible processes. To see what physically this could mean, just simply we would answer this question. Why a process should be possible or impossible. Why should a process be possible or impossible? Now, what we do is to take a sample case. This is a body with temperature Ta, and this is another body with temperature Tb. We all know that if Ta is larger than Tb, heat transfer would be in this direction. And the larger it is, the stronger this heat transfer would be. If Tb is larger than Ta, then the heat transfer would be in the opposite direction. And the larger this difference is, the more heat transfer would be. So this is where the possibility of a process is defined. Now, if Ta equals Tb, what does that mean? That means, first of all, and in reality, that there is no heat transfer. Or it means that there is as much incentive for a heat transfer from Ta to Tb as it is for Tb to Ta. So, what we call this process, we call such a process a reversible process. A reversible process. What is a reversible process? A reversible process, a reversible process is the one that could be reversed, that could be reversed with no change in the system or environment, or the environment. You see, if I lift this pen, I could always return it to where it was. But the system has returned to where it was. But the environment hasn't. I am more tired. If we heat this room, we could leave it to cool down. But the system has returned to where it was. The environment hasn't. You see that it's a pretty impossible process. In fact, I only know processes which are at least uh, theoretically and even more in practice proved possible and reversible. I will tell you a bit later on about that. But this is the borderline between possible and impossible processes. This is the reversible process, and it is almost always impossible itself. What's the other incentive for a process to take place? Assume that there is a temperature pressure difference. So assume that there's a wall and we have here PA and here we have PB. Both exert pressure on the wall. If PA is larger than PB, then the wall would go rightways, left rightwards. And if PA is smaller than PB, the wall would go leftwards over the partition. But if PA equals PB, it could go both rightwards or leftwards. So this would be a reversible process. It's a process with minimum incentive to be possible. You see, the larger PA is, the stronger would be the force to move this partition to the right. The larger the PB would be, the stronger would be the force to move this partition to the left. But if they are equal, that is the minimum incentive for a movement of the partition. And that we call a reversible process, a process that could be reversed with no change in the system or the environment. Almost always impossible and pretty fictitious. What else could be? So we have already known two uh, um, two incentives which make a process possible or irreversible. One is heat transfer in the presence of a temperature difference. Two, expansion in the presence of a pressure difference. The third thing that makes it always resist every process is friction. Friction is something that can't be reversed. In fact, if you reverse a process, the friction would still be there. It wouldn't give you back what it has already taken. So friction is also one item, one element, one fact which makes a process irreversible. Four is combustion. Burn a matchstick, it won't return to its original place. Burn fuel, you can't return it to its original situation. So combustion is pretty irreversible and also possible. And finally, five, mixture. Mix two items, whatever you want. Mix beans with rice. To separate them, you have to do work. Mixture is irreversible, and if you mix, then you have to separate. how much difference should be. I mean, if you mix 2 dishes of rice, well, uh, if you can distinguish between the 2 dishes, then entropy is not increased because you can always put a line in between and they are just like before. So entropy increase would be important so long as you can differentiate between the 2 items that you have mixed. These are the 5 elements in a process which could make it irreversible and could make it possible. So, as it is, real processes are irreversible, they can't return because of that, they are possible. Okay, reversible process is the boundary between the two. There are 2 processes, as far as I have seen and experienced, which are reversible and can take place. Well, what they are. First one is a process which is internally reversible, reversible, and that is the process of boiling. What do they mean by that? They mean that a drop of water, which turns to steam, it happens at constant temperature. And so long as the process is happening at constant temperature and at constant pressure, then none of these incentives would be present. So that is internally reversible. The second process that I've come across, which is uh, reversible, is an expansion fan. Expansion wave. Why call it a fan? It's a Prandtl-Meyer fan, but call it a simple expansion wave. You see, when I push my hand forward, I make one compression wave. That compression wave moves forward and becomes a step change, becomes irreversible, even if I push my hand very gently. If I pull my hand back, I produce one expansion wave, and that expansion wave gradually becomes a longer wave and remains reversible, remains with very, very gradual steps. Further explanation of this one will be left to the class of gas dynamics and compressible flow. But at least it's good to mention here that there are 2 processes which could uh, be reversible, could be real and produce no entropy. Good. Thank you very much. In my next lecture, I will start solving problems and using this equation of second law, which I've gained to solve some problems to show the power of this equation. Thanks for watching. Cheers.